Okay, let's go ahead and take a peek at these questions. So for this question, we are looking at kids and toys. So in an experiment on the behavior of young children, each subject is placed in an area with 5 toys. Past experiments have shown that the probability of the number of X or toys that a child will select is as follows. So the chance that a kid picks none of the toys is 0.03 or 3%. The probability that kids pick one of the 5 toys is 0.16, so on and so forth. Is this a discrete random variable or continuous? So we have to think, are we collecting just one value and then there's another option and we're not thinking about anything in between, or are we thinking of all the possible values that could fall in between my different points? So in this case for part A, we would say this is discrete because we are using toys and we have set values for number of toys that can be selected. I can choose 0 toys for 1 toy and nothing. And actually we accept no values between 0 and 1 for X. So I can't have 1.2 toys. It's not an option. So for part B, describe in words what is meant by this statement. So P means probability. So for part B, P of X equals 5 means we are looking for the probability that X is equal to 5 toys. So what is the, or you can word it this way, what is the probability that a child will select all 5 toys? And then we have to find it. So for this one, what you'd want to look at is that this is it's a table. So if it's a valid model, then all of my options should add up to 100%. So there's only one I don't know. So if I want to go ahead and just add up all the probabilities I do have, so if I take points, I'm going to add up all these numbers. So 0.03 plus 0.16 plus 0.3 plus 0.23 plus 0.17 equals 0.89. So if I add all of these up, this whole part of the table is a 0.89. Oh, there go the lights. 0.89. And then there's only one thing left I don't know, and it should all add up to 1. So the probability that X equals 5 is going to be 1 minus 0.89, which is 0.11. And this would be your work. Okay. For part C, what's the probability that a randomly selected subject, so child, plays with at most 3 toys? So the probability notation is given here. X is less than or equal to 3. So at most, you're going to play with 3 toys. So it could be 0, 1, 2, or 3. So for this question, we just want to add up the options that we're interested in. So these options here. So for part C, you're taking 0.03 plus 0.16 plus 0.3 plus 0.23 is going to give you the probability of X being less than or equal to 3. And you can find that on your calculator. Okay, for this question, we are looking at choosing a person that's age 19 to 25 years at random, and we asked them a question. So in the past 7 days, how many days did you work out? So their response is what we're collecting, and that is the number of days that we're looking at. So we're going to call it Y, is the number of times that somebody worked out in the last 7 days. So we can have 0 through 7 as our options for Y. So this would be another discrete thing because I'm just accepting like you worked out 0 times, 1 time. I'm not accepting anything in between. So based on a large sample survey, here's our results. So for part A, a histogram of the probability distribution is shown. So this would definitely be a right skew because things are slanting down. And then we have a major peak here at 0. So most people in this distribution have worked out 0 days. That's where we're peaking. So then what we want to do is calculate and interpret the expected value. So that's just our average. So that our formula for that technically is you have your X value and you multiply it by the probability it goes with, then you add all those together. So you don't need to show the formula, but technically this is what you're doing. So if we want to use notation, the mean or expected value of Y equals 0 times 0.68 plus 1 times 0.05 plus, I'm going to put ... and then 7 times 0.02. And you're going to get that number. So if you go ahead and multiply that, there's a lot to multiply there, but technically that is what you would do to do this question. So if we multiply all of the things by typing it into our calculator, takes a hot second, but you can also use the calculator trick if you want, which is putting things in a list. So if you do want to use that shortcut, there's the video back at the beginning on the resources page, resource slide. Okay, so I get a number that doesn't make tons of sense. Hold on. Yeah. This thing is 0. Okay. Okay, so there we go. So my answer that I got is 1.71. So in order to interpret this, I'm going to save you, spare you my handwriting, but in order to interpret this number, we would say we expect a randomly selected person to have worked out 1.71 days if we asked many people. So on average, people work out about 1.7 days, which makes sense because we've got a lot of people that don't work out, but then we have still some probability for each of the other days. So it should be pretty close to 1 day, but it's going to be a little bit more than that because we do have some people working out more frequently up here. So that's this question. Okay, so let's go ahead and read this one. This is dealing with household size. So in government data, a household consists of all occupants of a dwelling unit, while a family consists of 2 or more persons that live together and are related by blood or marriage. So all families form households, but some households are not families. So basically some people might live together, but they're not considered a family because there's no marriage or blood relation. So like, if you're living together with your college roommates or something, you would be a household, but not necessarily a family, unless you're related to one of your random roommates. So here are the distributions of household size in the US. So we're gonna let X or H equal the number of randomly selected US households. So people just residing under the same roof. And F is the number of randomly selected families. And this is the distribution of the number of people either in your household or in your family unit. So we're going to compare and contrast these two. So in terms of comparing and contrasting with probability distributions, we're mostly just looking at the shape and where it peaks. So for this question, for part A, what I'm looking at is both distributions follow of household or family size follow a right skew, which is kind of popular with these. The family, or we could say the distribution of X peaks at 2 people per household, and H peaks at 2 as well. So they're pretty similar in terms of where they're peaking in their shape, but we can also say there's one difference. When we look at H, or household, there are some households of size 1, whereas F, there are no households of size. So that's kind of what you want to do. It's just a basic compare and contrast. Your two things you're looking at usually are where you're peaking and what your shape is. So we want to find the expected value for each of the random variables. We're going to interpret the values and explain why the difference makes sense. So I'm going to show you kind of how to set this up and then explain the difference. But I don't want to take all your time watching me put things in a calculator. So here's how you would do it though. So let's just kind of like show you the setup. So for H, remember we're taking the value and multiplying it by its probability. So here you can just kind of estimate these is fine. And as long as your estimate is reasonable and you're writing down your work, that's okay. So for me, so let's do notation. So the mean of X, H, you're going to take your values 1 and estimate roughly where this is. So I'm going to say it's 1 times 0.25 plus the next one 2 and where it's at about 0.3 plus the next one, the next one, the next one. So you're using where the bar is times how tall it goes for each of those. So then same thing for, and you're going to add up, multiply, add all those up, get a number. Family starts at 2, so I would say 2, and then there's about, this is at 0.4 plus the next value is 3. I would say at about 0.2. You can do reasonable estimates for these plus, and then make sure you go all the way up to 7 for each of those to get your numbers. Now, why are these different? Why would it make sense that these are different? So let's interpret first. So we would say the expected amount of people that live in a randomly selected U.S. household is whatever we find here for H. And then if we select many, many households. And then for F, the expected amount of people living in a randomly selected U.S. family is, fill in the blank with whatever this number ends up being, if we select many, many family houses randomly in the U.S. So why are these different? Well, it's going to come down to the definition, because a household, you can just have single people living by themselves, but a family generally has a set of parents usually, or a parent and children. So there's generally, if you're considered a family, you're related by blood or marriage. So based on the definitions here, that's why it makes sense that there's a higher expected amount for families than there is in households, because households, again, you can have just one single person living there. So then for the standard deviation interpretations, basically we want to think about why these two are varying more or less. So when we're thinking of a household, we have this number 1.412. So we would say a household size typically varies from the mean value of fill in the blank from whatever you get for B by 1.412 people. A family size typically varies from the mean of whatever it is from part B by 1.246 people. So then again, in terms of the context, why does it make sense that the families would vary less? Well, you've got less options generally by the definition, because you can't really, one person living by themselves is not considered a family unit because there's only one person there. You're not living with people you're married to or blood relatives. So since we have less options to choose from, there's no chance that I'm going to have a 1 in there. There's less data factoring into that calculation for the family unit. So the data is a little more clumped because we don't have the 1, we don't have the single individuals in that definition. So it makes sense that the family variation would be a little bit less than the people that are in households, because it's a little bit broader of a definition and what we accept for the number of people in those households.